In this video lecture, I want to talk about L'Hopital's rule. L'Hopital's rule is a way to find limits when we have what's called an indeterminate form. So first I want to take an example from some of our basic limits that we did in Calc 1. Something like this, where I have x squared limit as x approaches 2 of x squared minus 4 over x minus 2. So notice if I put in 2 for x, I'm going to get 0 over 0. And that is considered an indeterminate form. I think a lot of students want to say that that equals 0. And I just want to put a big red X through that. That is not true. That would only be focusing on, I kind of say, well, if there's 0 in the numerator, then it has to equal 0. But that's completely ignoring the denominator, which tells us that anything that when we divide by 0, that's undefined. So that doesn't mean the limit doesn't exist, but we do know that the function is undefined at this point, right? Because there's no value here. So the question is, well, how do we evaluate this? Well, we have some techniques from Calc 1, just some algebraic techniques that allow us to evaluate this. We could factor the numerator, so we would get x minus 2 times x plus 2 over x minus 2. And then we cancel this factor, and then we end up with the limit as x approaches 2 of x plus 2. Now this function is continuous at x equals 2, so we can evaluate it by substitution. Remember, continuity means that the function value and the limit are the same. So we can evaluate the limit simply by evaluating the function. So I can put in 2 for x, and the limit's 4. So again, I want to emphasize the function is undefined at x equals 2. But it's algebraically equivalent to a function that's continuous at x equals 2, and we can use that to find the limit. Now, the issue is, what happens when we end up with something like this? So notice, again, we have something similar. If I put in 1 for x, natural log of 1 is 0. And if I put in 1 for x in the denominator, I get 0. But there's no way, I mean, I can factor the denominator, but that's not going to, neither of those, that'll be what, x plus 1 and x minus 1, neither of those will cancel with natural log of x, so that doesn't help me at all. So L'Hopital's rule is a way to deal with these indeterminate forms. And these aren't the only indeterminate forms. I'll talk about others in a moment. But first, let's kind of state what L'Hopital's rule tells us. It tells us that if I had the limit as x approaches c of some function over another function, all right, is indeterminate. It's indeterminate. And again, we'll talk more about, but here's one example. We could also have infinity over infinity. Those are the two common ones. The other thing I should point out is it has to be indeterminate of the form 0 over 0 or infinity over infinity. There are other indeterminate forms that can be manipulated into one of these two forms. We can only apply L'Hopital's rule if I have something that's indeterminate of the form 0 over 0 or infinity over infinity. Then this limit equals the limit as x approaches c of the derivative of the numerator and the derivative of the denominator. All right, so in other words, the limit at this point of the ratio of the derivatives will equal the limit of the ratio of the functions. So let's look at first how we could apply that to this one over here. We've already done this, but and we did it algebraically. But let's show that we would get the same limit if we use L'Hopital's rule. So let's take the derivative of the numerator. So this is the limit of this. We're going to come down here. So this is going to equal the limit as x approaches 2 of the derivative of x squared minus 4, which is 2x, over the derivative of x minus 2, which is 1. So now this is continuous. I can just put in 2. When I put in 2 for x, I do indeed get 4. All right, let's do this one now. So I'm going to take this and bring this down here. And so let's take a look at this one. So now I'm going to use this This just means it's equal by L'Hopital's rule to the limit. But it's not exactly the same limit, but it has this. It's not the limit of the same function, but the limit will be the same as this one. So derivative natural log is 1 over x. The derivative of x squared minus 1 is 2x. So after I simplify, I get 1 over 2x squared. So the limit as x approaches 1 of 1 over 2x squared. I can just plug in 1, and I'm going to get 1/2. All right. So one thing I want to point out here, why, without deriving L'Hopital's rule, why does this make any sense? And ultimately, it goes back to what we know about derivatives. Derivative is the rate of change. So while natural log goes to 0 as x approaches 1, and x squared minus 1 goes to 0 as x approaches 1, they don't necessarily go to 0 at the same rate. And this is where the derivative comes in. This tells us the rate at which natural log of x is changing at x equals 1, and the rate at which the x squared minus 1 is changing at x equals 1. And so the ratio of those rates can give us the limit of the ratio of the two functions. Okay, so what I want to do now is just look at some other indeterminate forms and go through a few more examples. All right, so as we said before, 0 over 0 and infinity over infinity are indeterminate forms. The rate at which the functions go to 0 or the rate at which they blow up to infinity might not be the same, and so the limit could exist. Furthermore, these are the forms that we have to work with. We have to have a limit of one of these forms before we can apply L'Hopital's rule, because we could also have 0 times infinity. All right. So again, one of them is going to 0, because 0 times anything is 0. But infinity is not a number. So this thing, one of them would be blowing up really fast. You know, well, maybe not really fast, but either way, it increases without bound, while the other one goes to 0. So again, the question is, which one goes faster? Does the one go to 0 faster than the other one blows up to infinity, or vice versa? Because that will affect the limit. We could have 1 to the infinity. So on one hand, we know that 1 to any power is 1. But how fast is the exponent going to blowing up to infinity, and is it fast enough for the limit to not equal 1? We could have 0 to the 0. So again, we have a rule that says 0 to any power would be 0, but we have another rule that says anything to the 0 power is 1. So again, it depends on the rate at which each of those functions are going to 0. Infinity minus infinity, again, depends on the rate at which each of the functions are going to infinity. And finally, infinity to the 0 power. Right? So on one hand, you would think if the base is blowing up to infinity, then the whole thing is going to go to infinity. But of course, we also know that anything to the 0 power is 1. So again, it depends on the rate at which each of these functions is going to these respective limits. So let's look at a few examples. Let's look at the limit as x goes to infinity of x over e to the x. All right. So we know that each of these individually, they're going to go x goes to infinity as x goes to infinity, and e to the x goes to infinity as x goes to infinity. So we apply L'Hopital's rule, since we have this. These are the two forms we need to apply L'Hopital's rule. If our limit is in one of these forms, we can apply it directly. So the derivative of x is 1. The derivative of e to the x is e to the x. So now I take the limit as x approaches infinity. All right, so the denominator grows without bound, while the numerator stays 1, so that's going to go to 0. And again, this just shows that e to the x goes to infinity much faster than x does. And so as their ratio goes to infinity, the limit will go to 0. All right, what about, let's do another example. What about if we took the limit as x approaches infinity of x squared? Well, we know x squared goes, that increases faster than x, right? So again, we have infinity over infinity. We can apply L'Hopital's rule immediately, right? So the derivative of x squared is 2x, derivative of dx is e to the x, and, whoops, end up with infinity over infinity again. Well, notice, this fits one of the forms that we need in order to apply L'Hopital's rule. So we can apply L'Hopital's rule again to this function. So let's do that. We have the limit as x approaches infinity, and now I take the derivative of 2x, that's 2, the derivative of the x, still e to the x. So again, 2 is constant, e to the x blows up to infinity, so this whole ratio will go to 0. And in fact, we could show that x to the n divided by e to the x, if this was x to the n over e to the x, it doesn't matter what n is, because when I keep applying L'Hopital's rule to e to the x, I will always get e to the x, and every time I apply the derivative to x to the n, it gets 1 degree lower, 1 degree lower, 1 degree lower, and it'll end up being a constant. So e to the x is going to basically grow to infinity much faster than x to the n, so that limit will also always be 0. So that's one part of the point of this example, but the other part is to show that you can apply L'Hopital's rule more than once. If the resulting limit is also indeterminate, then you can apply L'Hopital's rule again. Okay, let's look at another example. Let's look at the limit as x approaches pi over 2 from the left of secant of x minus tangent of x. So you have to remember your trig functions and maybe think about what the graphs of each of these looks like. But as we approach pi over 2 from the left, secant goes to infinity and so does tangent. So I have this infinity and infinity. Now this is where I want to emphasize I cannot, even though infinity minus infinity is an indeterminate form, I cannot apply L'Hopital's rule right now. I need to rewrite this so that it looks like one of these. All right? So what I'm going to do first is, well, we'll just rewrite this. And let's think about what secant is. Secant is 1 over cosine, and tangent is sine over cosine. So if I rewrite it that way, notice I have a common denominator, so I can rewrite this as the limit as x approaches pi over 2 from the left of 1 minus sine x over cosine x. So now let's think about what's going on when I put in pi over 2. I have sine of pi over 2 is 1, cosine of pi over 2 is 0. So 1 minus 1 is 0, cosine of pi over 2 is 0. So now I have the indeterminate form that I need to apply L'Hopital's rule. I have this 0 over 0. So let's apply L'Hopital's rule. We take the derivative of the numerator, the derivative of the denominator. So now this is, by L'Hopital's rule, limit as x approaches pi over 2 from the left. The derivative of 1 minus, well, derivative of 1 is 0, derivative of sine is cosine, so that's going to be negative cosine of x over the derivative of cosine, which is negative sine. So again, cosine of pi over 2 is 0, sine of pi over 2 is 1, so I get, well, the negative doesn't matter with the 0, and that's going to be negative 1, so that's 0. So if we go back to our original, we said, well, which ones, are they going to infinity at the same rate or different rates, and how does that influence the limit? Well, this basically, so I want to be clear, infinity minus infinity isn't 0, but what all this work has done is to show us that secant and tangent, as x approaches pi over 2 from the left, secant and tangent blow up to infinity at approximately the same rate, so that their limit would be 0. Okay, we have one more example, a little bit more complicated, that I want to go through, and it is a different indeterminate form that we haven't looked at yet. So let's look at the limit as x approaches 0 from the left of sine of x to the x. All right, so this gives us a 0 to the 0 form. All right, so what we need to do is think about how we can rewrite this so that we can come back to one of these two forms, the 0 over 0, the infinity over infinity. So the first thing we're going to do is we're going to leverage a property of logs. Remember that e to the natural log of a function is just equal to the function. This is just an identity, because natural log of a function is basically e to what power gives me that function. And if I raise e to that power, well, then it gives me that function. I mean, that's kind of the definition of an identity. So what we want to do is we're going to rewrite the limit as x approaches 0 from the right, sine of x to the x, as the limit as x approaches 0 of e to the natural log of sine of x to the x. All right. Using this identity, this limit and this are the same. And because e to the x is continuous, this is going to equal e to the limit as x approaches 0 of natural log of sine of x to the x. All right. Well, this seems kind of complicated. Why would we do this? Well, because of the property of logs that allows us to take this and bring it out front. So this is important. Let's not lose track of this. Notice I've taken the limit now and I've now put it up in the exponent because, again, that's because e to the x is continuous. We can do that. But it allows us to evaluate this limit. It's just that when we're all done, we need to go back and make this limit the power of e to find what the limit of our original function is. So let's just work with what's in the box here. I'm going to bring the x out front, so I've got limit as x approaches 0 of x times the natural log of sine of x. So again, this is why I got this ln involved to begin with, is so I can rewrite this way. Now, if I just look at this, I end up with a different indeterminate form. X goes to 0 times, well, natural log of sine of x. Well, sine of x, as x goes to 0, sine of x goes to 0. Natural log, as this goes to 0, natural log goes to negative infinity. All right, so this is, if we go back to our different indeterminate forms, this is of this form. So it doesn't really matter if it's positive or negative infinity, but the point is one of them is going to 0 and the other one is either increasing or decreasing without bound. So what we need to do is we need to rewrite this so that we need to rewrite this limit in terms of 0 over 0 or infinity over infinity, so we can apply L'Hopital's rule. So what I'm going to do, notice that multiplying by x is the same thing as dividing by 1 over x. So I'm going to rewrite this as natural log of sine of x over 1 over x. All right. So now I'm going to end up with, so the numerator goes to negative infinity. As x goes to 0, then 1 over x goes to infinity. And again, we don't worry about the signs so much. I have infinity over infinity scenario, so now I can apply L'Hopital's rule. So this is going to be the limit as x goes to 0. And we need to remember how to take the derivative of something like this. So what we need to remember here is that the derivative of natural log of a function, so I'll just put this over here as a reminder, the derivative of natural log of a function is the derivative of the function over the function. All right, that's a consequence of the chain rule. So you should have seen that before, but we're going to apply that to sine. So the derivative of sine is cosine, so the derivative of natural log of sine is cosine over sine. So I'm going to have cosine over sine in the numerator, and then in the denominator, the derivative of 1 over x is negative 1 over x squared. So let's see what happens now. If I put in 0, this is 1 over 0. That's basically, it's undefined, but it approaches infinity. And this is negative 1 over 0, so that also approaches infinity. So we could try to apply L'Hopital's rule again, but first let's see if we can clean this up algebraically, because that's sometimes a better thing to do. First, see if you can clean it up and get a different limit before you apply L'Hopital's rule again. So I can rewrite this. I can basically take this to the denominator and make it sine over cosine, right? We can divide by the reciprocal. And likewise with the negative 1 over x squared, just bring that up and make that negative x squared. Well, that actually is equal to negative x squared over tangent of x. All right, so now I have, now as x goes to 0, the numerator goes to 0, and the denominator goes to 0. So now I can apply, I have a form that I can apply L'Hopital's rule to again. So let's apply L'Hopital's rule. The derivative of negative x squared is negative 2x, and the derivative of tangent is secant squared. So now as x goes to 0, I get 0 over, and secant of 0 is 1, and then we square that, so we still get 1. So this limit is 0. Okay, that's a lot of work. Remember, though, I want to really highlight that this is that limit. So in order to actually finish this off, we need to make this the power of e. All right, so that this is going to be e to the 0, which is 1. So that is our original. Going back to our original, we said limit as x approaches 0 from the right. So I guess I lost that throughout. But this limit is going to be equal to 1. All right, so this shows one way to deal with if we have basically an indeterminate power, that we can use this property of logs to rewrite the function. And then we focus on this limit here. We go through, there's a couple different scenarios that we went through in terms of indeterminate forms and trying to rewrite it in terms of an indeterminate form that we could apply L'Hopital's rule to. I pointed out here, sometimes what we want to do is first simplify it algebraically and see what we have before we apply L'Hopital's rule again. We did that. We applied L'Hopital's rule. We got our limit. We put that back in as the power of e to find the limit of the original function. So again, this is a more complicated example, but it shows a lot of different techniques that you might use while working with L'Hopital's rule and indeterminate limits.